In this video, I will be going over the structure and function of the horse's gastrointestinal tract. I will be talking about the digestion of 4 different feeds and going over 2 feed plans I have created using Dengi horse feed. The gastrointestinal tract starts with the mouth, which contains the lips, teeth, and tongue, which aid in prehension of food, mastication, and swallowing. In response to mastication, saliva is produced and released by the portoid gland. Saliva's function is to soften and lubricate foods. Once food has been masticated and lubricated by saliva, it has been formed into a food bolus. Once food is swallowed, it travels down the esophagus, which is a tube-like structure. It starts at the caudal point of the oral cavity and finishes at the cardiac sphincter of the stomach. The esophagus lies dorsally to the trachea and extends through the thorax and diaphragm. The esophagus has both striated and smooth muscle that functions in a series of contractions and relaxation, known as peristalsis. Peristalsis is how food boluses are transported along the esophagus to the stomach. After travelling through the esophagus, the food bolus reaches the stomach by passing through the cardiac sphincter. The stomach of the equine is very small in comparison to their size, only holding 8 to 15 litres on average. Due to the small size of the horse's stomach, food does not stay there for very long, with the average being only 20 minutes. The stomach is located in the cranial abdominal cavity, within the protection of the rib cage. The cardiac sphincter is thick and well developed, meaning that it is very rare that horses can regurgitate any food. This can be problematic if the horse consumes anything dangerous. The interior of the stomach is split into 3 sections called the fundus, the body, and the pyloric part. Although there are these 3 sections of the stomach can also be split into 2 sections, which are the glandular and non-glandular sections. The non-glandular section is found in the fundus and part of the body. The glandular section is found in part of the body and the pyloric part of the stomach. These 2 sections are divided by the margo plicatus. The glandular section is covered by different types of secretory glands that produce and secrete gastric juice. Gastric juice is a mixture of mucus, hydrochloric acid, and enzymes. The hydrochloric acid neutralizes any harmful pathogens to prevent infection, whilst the enzymes function to start breaking down food material. Enzymes are proteins that act as biological catalysts and are all produced to break down specific food molecules, so they become small enough to be absorbed into the blood and lymphatic system. The enzyme present in the stomach is called pepsin, and its function is to break down proteins. The digestion of proteins in the stomach is very minimal due to the food being in the stomach for such a short period of time. When food is ready to leave the stomach, it passes through the pyloric sphincter, but before this, bicarbonate is secreted into the stomach to neutralize the acid to avoid damage to the small intestine before it enters. The small intestine runs from the pyloric sphincter of the stomach to the cecum of the large intestine and is split into 3 sections. These 3 sections are called the duodenum, jejunum, and the ileum. The functions of the small intestine include transportation of food and secretions via peristalsis, the secretion of intestinal fluids that allow digestion, the mixing of the food and intestinal fluids, and the absorption of food and fluids into the blood and lymphatic vessels. The intestines have small finger-like projections called villi that increase the surface area of the small intestines that then maximizes the intestine's ability to absorb nutrients from the digested food. The intestinal fluid contains enzymes called amylase that break down starch into sugars, protease that break down proteins, and lipase that breaks down fats. The intestinal fluids also contain bile salts that emulsify fats, neutralize acid from the stomach, and stimulate lipase secretion from the pancreas. The duodenum contains both the major bile and pancreatic ducts, while the duodenum is the main site of absorption. Absorption that occurs in the small intestine includes amino acids, glucose, minerals, and vitamins into the bloodstream, and fatty acids and glycerol into the lymphatic system. Once all of these are absorbed, the structural carbohydrates pass on into the large intestine undigested. To pass into the large intestine, food must pass through the ileocecal junction that is located at the end of the ileum. The large intestine of the horse has three main parts: the cecum, colon, and rectum. Once food has passed through the small intestine, it enters the cecum, which is a blind-ending, comma-shaped sac that acts as a holding chamber. This holding chamber acts as a fermentation vat where microorganisms break down cellulose into simpler carbohydrates. They synthesize essential amino acids and unlock some water-soluble vitamins. This fermented food is then passed into the large colon, which consists of three parts: the ascending, transverse, and descending colon. The two important functions of the colon are to store and absorb fluid and to retain food material for microbial digestion. Food material goes through microbial digestion mainly in the dorsal and ventral colons. During this microbial digestion, insoluble carbohydrates are converted into volatile fatty acids called acetic, propionic, and butyric acid. These volatile fatty acids can then be absorbed. Food material is then passed through the small colon that connects the large colon and rectum. In the small colon, further absorption of fluid occurs and food material is turned into fecal balls. The fecal balls are then passed through the rectum, which is the continuation from the small colon to the pelvic inlet, where it finishes at the anus, where the fecal balls are expelled. Ailey's Best British Oats contain 12 to 15 megajoules per kilogram of digestible energy, 11 to 13% protein, 3 to 5% oil, 10 to 12% fibre, and 1 to 3% ash. The protein in oats is of a high quality and will be digested in the small intestine. The protein in oats has a high level of all essential amino acids for horses except lysine and threonine. Oats are a quick-release energy feed, so contain a high quality of simple carbohydrate. Because of this, most of the carbohydrate content in oats will be digested and absorbed in the small intestine. This quick-release energy will then go on to be used for anaerobic energy. Micronized linseed contains 23% crude protein, 39% oil, and 20 megajoules per kilogram of digestible energy. Linseed provides a good balance and availability of amino acids in its protein and is only beaten by soya. Linseed is high in oil, which is fat. This is why linseed is considered very good for coat condition. Linseed contains high levels of starch and sugars, which provide anaerobic energy. Soybean meal contains 15 megajoules per kilogram of digestible energy, 50% protein, and 7% fibre. Soybean meal is considered a protein supplement due to having such a high quality protein with balanced levels of amino acids, yet high levels of lysine. It is not a great provider of energy but does not contain a lot of complex carbohydrates, meaning that soybean meal is predominantly digested in the small intestine. Sugar beet contains 12 megajoules per kilogram of digestible energy, 9% protein, 0.7% oil, and 16% fibre. Sugar beet contains complex carbohydrates that provide aerobic energy, and it contains low levels of sugar and starch. Due to this, the carbohydrates of sugar beet will predominantly be digested in the large intestine. Sugar beet is not a great provider of digestible protein and is low in protein in comparison to feeds such as linseed. For my first feed ration, I did a 13-hand high pony that was 15 years old, overweight, with a history of suffering from laminitis. I estimated the pony's weight at 300 kilograms, and from this I could calculate the pony needed to eat 4.5 kilograms a day and consume 50 megajoules of digestible energy a day, with 404.7 grams of crude protein, with a ration of 70% forage and 30% hard feed. If this pony lived out on mature grass, the highest energy intake it would receive would be 10 megajoules per kilogram. On this calculation, if the pony was allowed to eat 3.15 kilograms a day of grass by restricting its consumption, it would eat 31.5 megajoules of its energy intake in grass. You would then supplement this by giving the pony 1.35 kilograms of Denji's Alpha Beet, which is Laminitis Trust approved. This would give the pony a total consumption of 46 megajoules of energy a day, which would only be slightly under its daily requirement. When I worked out the protein content based on average grass protein content and the protein content of Alpha Beet, the pony's protein consumption was way over the needed amount, but this was just in the grass alone. Due to this stress put on the kidney, a supplement will want to be added to support kidney function. The next feed ration I calculated was for a 15 3-hand high 3-year-old thoroughbred flat racehorse. Estimating that the horse weighed 450 kilograms, I calculated that the horse would eat 9 kilograms a day, with it needing 119.2 megajoules of digestible energy and 726.3 grams of protein. Feeding this horse on a ration of 50% forage and 50% concentrates, I worked out that it would have very close to its nutritional requirements on haylage and Denji's Alpha A oil. Its haylage consumption would give the horse 51.75 megajoules of digestible energy, and the Alpha A oil would give it 56.25 megajoules of digestible energy, giving a total of 108 megajoules of digestible energy. Due to this being slightly under, a need of supplementation with oats would be required. As for the horse's protein requirements, this diet gives slightly too high a protein content, so once again supplementation to support kidney function would be required.